Okay, this is a tutorial on deflection of trusses. Class are all behind me. So, you guys, you've done the topic already, I take it, and this is to help you through it. Deflection of trusses is basically two things. You have to work out the forces in the truss, and then the force in every member. And because in a pin-jointed truss, every member is only compression or tension. There's no bending in each member, in an individual member. When you have that compression and or sort of tension force, that means every member in the truss either grows or shrinks a little bit. And because it grows or shrinks a little bit, it changes shape, and that is the deflection. Okay? So we'll do an example. If we have a truss, okay, this is where my whiteboard goes wonky, because there's no eraser. So let's do a truss like this. All right. Okay. If we have a truss like that, now, sorry, let's go back and re-emphasize a few things. We are assuming this is a pin-jointed truss. So every member is connected with a pin, so it can take rotation at each end, and any load, we'll put a load right here, any load is only applied at the node, okay? Those are really important assumptions for this because things change if that's not the case. If you go on the railway network in Sydney, you will find some old pin-jointed trusses, but when you actually look at most trusses in real life, instead of having a pin joint, they're actually bolted together, and you think, well, that can't take any rotation. Okay, that's a solid jointed truss. It's more complicated to analyze, and we normally use tools like space gas and things like that. Okay, so pin jointed trusses. If we take just that member looks a bit like that. It's got a pin there. It's got a pin there, and there's no loads applied in the middle of the member. Okay, that means that if a load gets applied there, and the load gets applied there, you know, whatever other loads like that, there's no way for that member to go into bending, okay? Because it's like this is the member and you're pushing on the ends. There's no way for me to bend that pin if I can't control rotation there. I can only bend the pin if I grab it like that and do it like that. Does that make sense? Okay? So every member of that truss only has tension or compression in it. All right? So, we know from geometry the length of those members. What we do is we analyze that so we get a reaction. Whoa, that was cool. We get a reaction force there. We get a reaction force there. If there's any horizontal forces, they get taken up there. And we can work out the forces in this thing. And we'll know that that's going to have a compression, that's going to have a compression force at the top there. It's going to have tension in that one, tension in that one, tension in those, and that's going to be 0, and that's going to be 0. All right. Have you guys gone through and done zero force members? Can you tell me why you know that's 0 and that's 0? No? Okay. Let me show you. If we have a truss, let's have a look at a piece of a truss like that, where there is a member coming down, a member coming down like that. So that's at 90 degrees. There can only be tension or compression in that. So let's put tension in that one and that one. Okay? That's only horizontal components, there's no vertical component. So if there's no vertical component there, unless we have a force hanging off that, we know that that's a 0 member. Okay? This one can only be in tension or compression. If it's in tension or compression, there's no, like that's only vertical component, it's only horizontal component, those have got to be 0 force members. Okay? Alright. So what happens is, alright, those 4 members are going to grow, that one's going to get shorter. Because that happens, the truss is going to end up in a deflected shape. And all we have to do, well, there's 3 steps. We've got to work out what are the forces in each member. Then we've got to work out how much does each member grow or shrink. And then we've just got to redraw it with a new length. Okay, and that's just the geometry problem. Okay, does that make sense? Okay, So, do you guys know how to analyze a truss? Yes.
Somewhat.
You know somewhat how to analyze a truss. That's good.
Moments.
Let's go over a bit of truss analysis. Okay, we'll go over a really simple one. Let's do a triangle. We'll make it equilateral just for the sake of it. Actually, no, let's make it a right angle triangle with the right angle there, so that's 90 degrees. Let's put a support there, and we'll put a roller support there. Okay. Jade, what's your favorite number? Single digit, please. 2. We have a 2 kilonewton force there. Okay. Does everyone agree that's a truss? It is, good. That is a pin to support. What forces do we have, what potential forces do we have there? Or potential reactions, I should say.
Vertical.
Yes. We have vertical. Any others?
Horizontal.
Horizontal, yes, very good. And this is a roller connection. What potential force, potential reactions do we have there?
Horizontal.
No, try vertical.
Just vertical.
Yep. Okay. Those are the reactions. We'll call that A, call that B, call that C. So we have R, A, H, R, A, V. So reaction A vertical, and reaction B vertical. Okay. And the lovely thing about engineering, or civil engineering I should say, is everything equals 0. Okay? The sum, because this triangle is not accelerating somewhere, we know that the sum of all the forces in every direction is 0. Everyone agree with that? Okay. So the sum of all the forces in the horizontal direction equals 0. We have, that load is vertical. We have no horizontal load, so therefore RAH equals 0. Happy days? Okay. The sum of our vertical forces is going to be 0. So the sum of the vertical forces equals 0. So we'll go up is positive, down is negative. So negative 2 plus RAV plus RBV equals 0. Everyone happy with that? Okay. So we also, as well as all the forces, the moments about any point are all 0. So if we take the moments about that point there, I always like to take around there because anything going through that doesn't produce a moment. So, yeah, let's put a dimension in for this triangle here. What was that? 5 meters. Everyone happy? Okay. 5 meters, that's halfway along, so that's at the 2.5 meter point. So, and our sign convention, anti-clockwise is positive, clockwise is negative. Okay? So let's take moments about there from that force, that is going clockwise. So it's negative 2 times, and that acts down that distance. Because it's a vertical force, I've got to take the shortest distance to that line, which is where it gets down to there. Okay? So 2 times 2.5, because that's the distance, 5 for 5. And then our reaction from B is going anti-clockwise. So plus reaction at B vertical times the distance, which is 5 meters, equals 0. Sorry about that. Everyone agree with that? 2 times 2.5 is negative 5 plus RBV, or 5 RBV 5 equals 0. RBV equals 1. All good with that? And intuitively, we can look at that and go, we've got a 2 kilonewton force pushing down. We've got one there. Obviously, we're going to have one there. Okay. Let's do another moment check. I'll show you why I'm doing this. That's moments about A. Let's do the moments about B. Okay. Pick moments about B because B is independent of that force there. So moments about B equals 0. So again, the force, that's going around this way this time. So positive 2 times 2.5, which is the distance from there to there. And we've got the reaction force A going this way. So that's minus 5 times A. Sorry, 5 is the distance times the force. And all that equals 0. So again, we've got 2 times 2.5 is 5 minus 5 times, I'll say force A vertical, reaction A vertical. Reaction A vertical equals 0. We'll see the RAV equals 1. Reaction A V equals 1. Okay. So that's 2, that's 1, that's 1. And now let's do the final check. Back to here, sum of the vertical forces, minus 2 plus 1 equals 0. Happy days. Okay? Now, we could have skipped that step and gone straight to there. The reason I like to do that is that becomes a check. Because here's the thing with trusses. If you mess up the reactions, you're finished. Nothing's going to work for you. Okay? So, it's always worth doing a check to make sure you got the reactions right. Okay. The number of times I've put stuff into my calculator wrong, you find your error if you go back and you do this check. Okay, it's worth doing. All right. So any questions on that so far? All right. All we've done so far is work out the reactions for this triangular truss. Now we want to work out the forces in each member. Okay. So we've got, what I want to do now, I wonder if I can just, this might work. All right, so to remind ourselves, there's our truss like that. I'm going to replace those reactions with a force, and a force. That was 2, that was 1, that was 1. Everyone happy with that? Okay, we are going to isolate the joints one by one. So let's take joint A first. If I isolate joint A, I have a force of 1 there. Okay, I have, that's a force, we'll draw it a tension like that, and a force like that. Okay, those are 2 unknowns, so I've actually chosen pretty poorly. Let's actually isolate joint C first. Okay, joint C, that's A there. Joint C, there's 2, and remember we had a 90-degree angle like that. Okay, and I'm going to draw as if it's a tension. What we're doing, we're cutting the members, we have to supply the internal force, which is either tension or compression. Okay? And that is C, so that is CA, and this member is CB. Okay. Now, can everyone see intuitively that actually if you're pushing down on those 2, it's going to be compressive force pushing back up? Okay? So we're going to get negative numbers for those. Alright? So, again, sum of all our vertical and horizontal forces is 0. So we've got, let's look at the vertical forces at C. Sum of the vertical forces at C equals 0. So we've got -2, and we've got whatever vertical component of that and vertical component of that equals 0. You agree with that? Okay. So the vertical component, let's do vector adding. The forces, the vectors are going to be the same angle as the member. Okay. We know that this member, because we've got a 90 degree there, we've got 45 degrees there. Okay. So we've got that force is made up of a vertical and a horizontal. That vector is made up of a vertical and a horizontal. All good? Okay. So the vertical ones, we've got -2 plus that equals 0. Okay? So let's go plus the force in AB, vertical, equals 0. Oh, sorry, plus the force in BC, vertical, equals 0. Okay? Alright, now let's have a look at the horizontal forces. The horizontal forces in C are 0. The only horizontal things are that and that. Okay? So by looking at those, I can tell you that you can say they're equal. You see that? Okay? I'll write down the force horizontal CB plus the force in the horizontal of CA equals 0. Okay? Because they're 0, those two are equal. Okay? Because those are equal, we know that actually CA and CB are equal. Okay? Do you want me to go over that again? Okay? So if those two are equal, we've got -2 plus 2 times whatever force is in the vertical equals 0. So the force in the vertical is going to be 1. Okay? So that is 1, and that is 1. Okay? And if we look at our geometry, we've got, if we add the vectors like that, we know that that's 1, that's 45 degrees. By the geometry, that is going to be square root of 2. So the force in that thing is going to be square root of 2 kilonewtons. Do you want me to go over that again? I skipped a few steps there. That's good. Good? Okay. So we all agree that the force in that member is 1.414 kilonewtons. Square root of 2 is 1.414. Okay? And we also agree that that one, the force in that is 1.414 kilonewtons. All happy there? The vague look, I'm going no.
Just to clarify, you got the square root of 2 from a unit triangle, right?
Yes. A square root of 2 because we've got a 45-degree triangle. If that was in fact over here in a different angle,
Yeah, it's true.
we would still have that these horizontal forces are equal, but because those would have different angles, we'd get different complete forces there. Okay? Yeah. You all good with that? Okay. So we've got a force there. Oh yeah, are they in tension or compression? They are in compression. So I like to actually label each member with compression or tension. Okay? You can do this with the sign convention, like positive is tension, compression is negative, and put positive and negative numbers. I like to be really clear about, is this in compression, is this in tension? And look at it until you figure out, are they in compression or tension? Okay? Look at this thing, you've got a force coming down here, those things are holding up the force, they've got to be in compression. Okay? So they're compression, let's look at the bottom member now. Remember we had this, and we have now 1.414, and that's actually made up of a 1 and a 1 that way. Okay? Add the vector 1, 1, and you get 1 square root 2. Yep. Okay. So now, some of our vertical forces. There's the 1, there's the 1. The vertical forces are all taken care of. The horizontal forces, we've got a 1 pulling off that way. We've got a force there as well. So that one, the horizontal forces all have to be 0. So that one is actually going to be -1. All right, let me do this around the other way. This is in compression, so I've done my arrows backwards. Sorry about this. Let me try and correct it. You know how I said I got 1 there? That's tension, so that's actually -1, because we know that this member's in compression. So we've actually got something pushing down on that, okay? That results in a horizontal force going that way. That means that needs a horizontal force going that way. That puts that in tension. Sometimes as I say this, I think, golly, this is a confusing way to explain it. So come back to me and say, Pete, you're an idiot. This is confusing. I don't get it. Do you get that? I'm impressed. This is good. You know, explained it really badly, but here you are. Okay. Everyone happy with that? Okay. So now, I'll get rid of that line there. No. Here we go. All right. So now we have, there's our triangle. We know that that has a force of 1.414 in compression. That has a force of 1.414 in compression. And that has a force of 1 in tension. We just calculated that. Everyone happy with that? All right. So we have worked out the forces in the truss. Okay? Now that's a fixed point. That's a fixed point. If we want to know the deflection, we have to know something about those members. We have to know their cross-sectional area, and we have to know their elastic modulus. Okay? So in any deflection question, you'll definitely be given the elastic modulus or material, and you can look up the elastic modulus and the cross-sectional area. Okay? When I say cross-sectional area, that immediately implies or assumes that the member is a consistent cross-section all the way through. Okay? So let's say those are little squares of aluminium like that, and that's got an area because, you know, we can know the dimensions of that, and that's got a value of E, which is the elastic modulus. Okay? And we know that the change in length, does anyone know this formula? We're getting close. So we're looking for the change in length. So we've got 2 terms at the top, 2 terms at the bottom. P L over AE. Let's see if that's right. That looks right. P is the force. If you put more force, your length changes. Yep. L is the length of the original. If your member is quite long, you get more extension. If your member is quite short, you're going to get less extension, so that's correct. A is the cross-sectional area. If the member is bigger, chunkier, it's going to give you less change in length. And E is how stiff it is. Again, if it's stiffer, it's going to give you less change in length. So that is the correct formula. Okay? Everyone happy with that? Okay, so we have just worked out the forces, all the P's. We have to work out the lengths next. We have to work out the length. That's a geometry problem. We'll be given the area. That's what, you know, the size of the members we're given, and the stiffness is the material property. So what I suggest you do then is do a table with the member. So member AB, BC, and AC, and do the length, and then the force, which is P. I think I could do this right first time. And then we're going to have the change in length. Okay? You work out that, you work out the P, you apply the formula, you get the change in length. Okay? And then after the change in length, you get L2. L2 I'm calling the new length. I'll write it down there. New length. Okay? Then when you've got the new length, then you have to redraw the truss with the new shape. Okay? So, this is A, B, C. Is AC going to get shorter or longer?
Shorter.
Sorry? Shorter, very good. Yes, both of you, shorter. Yep. So that's AB has got a negative value in it. BC, shorter or longer?
Shorter.
Shorter. And CA, longer or shorter?
Shorter. Longer.
Let's go with his answer.
CA. Oh.
CA, the one. Oh, whoa, sorry. No, AB.
AB gets.
Yeah.
AB gets longer. Sorry, guys. Alright, let's do that again. Alright. Delete 30 seconds. Okay. AB, from there to there, is it longer or shorter? Gets longer, thank you. AC, shorter, and CA, shorter. BC, sorry, shorter. Okay. Very good. And now, when you calculate those new lengths, you just have to draw that triangle with the new length of members. And because compared to that triangle, if I can do some another color. Okay, our new length AC is going to be slightly shorter. Our new length BC is going to be slightly shorter, and the AB is going to be slightly longer. That will be up to there, and that will go out there like that. That is the shape of our new triangle. Okay, because once you know the length, the triangle can only be a certain shape, right? So it's a matter of drawing the new shape. Now, there's a couple of ways to draw the new shape. One is to go wild with cosine rule and, you know, all sorts of geometry to do it. The other is you do it in AutoCAD, where you go, I need that length, so I draw a circle around A of that diameter. I draw a circle around B of that, or there of that diameter. Where those circles intersect, you know, to see the other points. And you draw the triangle that way. Does that make sense? Okay. So when you have a more complex truss, like this, you've got to go through the same process. You've got to work out the force in every member. So you've got to work out first the reactions, then the force in every member, then do this table, then get the new length, and then redraw that with the new lengths. Okay? There's one assumption built into this, which is, I was going to say barely worth mentioning, but it is worth mentioning it. If this only works if the change in length of the members is pretty small compared to the original length. Okay? The reason for that is if that changes a lot, then actually the geometry of your truss has changed, and therefore the forces change. Okay? This assumes that this deflected shape is so close to the original that all the forces are pretty close to the original. Okay? Because that is now no longer a 90-degree bend. That's going to be a little bit bigger. And because it's a little bit bigger, that's no longer 1.414, that's something else. Okay? So this is what we call a first order analysis, which is the deflected shape is close enough to the original that the forces are pretty much the same. Okay? A second order analysis would say, all right, we've actually got this new shape, let's reanalyze that triangle with that new angle and the slightly different shape. Okay? So this is when you talk about first order analysis, second order analysis. A program like SpaceGas will do a second order analysis, which means it does the first analysis, then it looks at the new shape, then it does the analysis all over again. And then it looks at the new shape and does it all over again. And it keeps doing that until the answers converge, until it gets to the point where it makes no difference anymore. Or, and this is where you have an unstable structure, it gets to the point where the structure actually collapses and the answers diverge and it says the structure is unstable, can't do this anymore. Okay? I can give you an example of, no I can't right now, the divergent structures. But some structures are really sensitive to the movement, some are not. Okay? I'll give you one example of something that is. If you had a flagpole and you put a vertical load on it and a little bit of a horizontal load and it bends over, okay? Now you've got a load on top of that. You can see that it actually puts more bending into the pole, okay? that is something where it's what we call a P delta effect, or the second order analysis is going to be really important. Okay, for something like this, especially when the member's quite stiff and the forces are low, first order analysis is going to be good enough. Okay, that's deflection of trusses. We can go through a problem if you like, or we can. That's the theory of it. What do you want?
I think a problem would be good. Like
Okay.
if there's more components involved.
Yep.
That's just a single.
Okay.
Ladder one involved in the actual topic, which is like 3 of them.
Okay. Let's have a look at the one on the topic. What does it look like?
Yeah.
It is a fancier triangle than one we had. So it's that, and then that, and that. And what are the letters?
So it says make 2.
Yeah, the second one's all workout, the first one's fine.
Yeah, right. Does that mean you do 2 different ones? Can you do 2 different ways?
And
to
so
do
we've
it,
got a
or
force.
2 different ways to draw it.
Okay, we've got a force hanging from there, and then we've got a horizontal force there.
Yeah, so I was thinking.
Okay, and then just a second, and we've got auxiliary reactions in there.
That's a pin joint. That's sorry. That's a right.
That's a roll on that side?
Yeah.
Yep. So that's what we've got, right? Okay. So the first thing you're going to do is reactions. Okay? We'll do a really easy reaction first. It's got one